students, in this video, we'll prove a term attributed to Napoleon, but was most likely not proven by him. So this is what's known as Napoleon's theorem. And what does it say? It says, given a triangle, ABC, what we're going to do is we're going to form three equilateral triangles on each side of the triangle. Form three equilateral triangles on the sides of ABC. Okay. Then the centroids of those new triangles themselves form an equilateral triangle. That's a lot of words, but let's actually draw a picture, okay? So here's my triangle. Okay, this is my A, B, and then C. That's my original triangle. Then what I'm going to do is I'm going to draw equilateral triangles. I'll try to draw this as best I can on all the sides, like that, and then like that, okay? And so this point over here is going to be C prime, this point over here is going to be A prime, and this point over here is going to be B prime. And we're going to look at the centroids of these things. So the centroids, I'm going to call this, let's call that one over here, let's call this one over here G1, G1. Let's call this one over here G2, and this one over here G3. And we can sort of see that if I connect these dots over here, since my rough drawing is pretty good, that triangle over there, that blue triangle in the middle over here is going to be an equilateral triangle, okay? That's going to be an equilateral triangle. So in other words, triangle, this means i.e. triangle from G1, G2, G3 is an equilateral triangle. Okay, excellent. That's Napoleon's theorem. So what do I want to do with this? Well, I want to prove a lemma first to make this a little bit easier, okay? So here's my lemma. Triangle, a triangle. Let's call that triangle DEF. Or let's make our life a little bit easier. Let's use some numbers over here. Let's say a triangle A1, A2, A3 is equilateral if and only if what? So let's think about this from another perspective. If I draw this triangle over here, let's think about this over here. So we have A, A1, A2, and A3, like so. Well, it's going to be equilateral if when I rotate this A2 about A1, I get to A3. So if and only if, how do we write that out? We get that A3, the complex number for A, the third coordinate, is really what? Is really the origin A1 plus what? Plus A2 minus A1, A2 minus A1, and then times zeta. And what is zeta over here? So zeta, where zeta is the exponential of pi I over 3, okay? Excellent. That's a trivial definition, right? Because if I rotate one side length 60 degrees to the other one, that automatically proves that this is a 60-degree angle, that those two side lengths are the same, and if that's 60, then that has to be the same. So in other words, you're equilateral if and only if this condition is true, right? Now there's one sort of modification we can make to this. What can we notice? Well, zeta, this is really what? This is really going to be 1/2 plus I root 3 over 2, right? And so now I really have A1 minus this. So 1 minus zeta, this implies that 1 minus zeta is going to be what? Is going to be a 1/2. So we're in the either first or fourth, then minus I root 3 over 2, right? And that's really zeta to what power? That's really zeta to the 5th power, right? So this is 1 minus zeta is really zeta to the 5th power, like that. Excellent. So that's an important thing to observe over here. Because now what I want to do is I claim that this is true if it'll be a certain relationship. So let me let now. The lemma is trivial. So if we let xc be zeta squared, then let's box star over here, star, then star is true if and only if what? If and only if a1 plus xc, a2 plus xc squared, a3 is equal to 0. Okay? In other words, this is the condition we're gonna use in Napoleon's theorem. Okay, so how do I prove something like this? Well, let's do it. So let's assume that star is true. Then I have a1 plus a2 zeta squared, because that's what xc is. Then I have zeta to the 4th, right? That's what xc squared is. And let's fill out what a3 is going to be. A3 is going to be an a1, and then plus what? So we really turn this into a what? The coefficient of a1 is what? The coefficient of a1 is going to be a 1 minus zeta. So it's going to be an a1 zeta to the 5th power, right? So zeta to the 5th power. Good. And then what? And then a plus a2 zeta, right? Plus a2 zeta. a2 zeta. Okay? Excellent. And now what's going to happen over here? So what we really have over here, so now zeta, xc is really what? So let's check this out carefully. So we have the following. So this is really equal to a1 and then a 1 plus zeta to the 9th power, right? And then what? And then a2, and then zeta squared plus zeta to the 5th. Zeta squared plus zeta to the 5th. Okay? Now what is zeta to the 9th power? Zeta to the 9th power is going to be e to the 3 pi I. E to the 3 pi is -1. So this is negative, that's 1 minus 1 is 0. And then that's going to be zeta squared times 1 plus zeta cubed. Zeta cubed is -1, so this expression is equal to 0. So excellent. So now we have that you can either check star or you can check pound, and you can reverse this reasoning. So either star or pound are equivalent to each other. Excellent. All right, so now what we're going to do is the following. So now we're going to write down the coordinates for G1, G2, and G3. So now what is G1? So G1 is really what? G1 is really B plus A prime plus C over 3. G2 is going to be what? Is going to be A plus C plus B prime over what? Over 3. And G3 is going to be what? And so here's the proof of Napoleon. Okay, maybe when he was stuck in exile, he proved this. I doubt it, right? So he was too busy trying to invade Russia and all that sort of jazz to be bothered trying to prove a geometry theorem, right? Even though famous historical figures from that century, from the 19th century, like Abraham Lincoln and Garfield, all took a crack at mathematics because mathematics is so important. It was necessary to be the president, right, in the United States to be good at math, right? That's not true anymore, but it used to be. Okay, cool. All right, so unless you want to vote for me for president, but don't do that. Whatever you do, that's essential. You do not do that over 3. Okay, good. All right, and so what do we need to check? We need to show that G1 plus what? Plus xc G2 plus xc squared G3 is equal to 0. If we can show this, then we have proven the theorem, right? So let me look at the quantity 3 times this expression, okay? So let me look at 3 times this expression. So 3 times the expression G1 plus xc G2 plus xc squared G3 is equal to what? Now, sir, it's going to be a whole bunch of terms, so let's just be very patient with this, right? So 3 times G1 is going to be what? Is going to be B plus A prime plus C plus xc times what? G2, which is going to be an A, and then plus C, and then plus B prime. Great. plus what? Plus a xc squared. Xc squared, then I have an a plus b plus c prime. That's exactly what we get. Now let me remind you what we have actually. So we have some more information. We know what? Well, I know that this is going to be what? I know that a prime b c, if I go from b to a prime to c, that's going to be an equilateral triangle. So I know that b plus xc a prime plus xc squared times c is equal to 0, because that's an equilateral triangle. I know that c plus xc b prime, c plus xc b prime plus xc squared a prime, a is equal to 0. And finally, I know that a c prime, so a plus xc c prime plus xc squared b is equal to 0. So those 3 bits of information I know over here. So let's keep working on this over here. So let's gather some terms over here. So the terms of a prime needs to have an xc over here. So what we can do is I want a straight b, a xc squared c, which I don't have, so and I need an a prime, okay? So we need a b, an a prime, a b, an a prime, and a c over here. So let's write out those terms over there. So those 3 terms, so what can I say about the a prime, the b, and then the xc squared c? So what we need over here is, let's write this out. So those terms are going to be helpful for me. So let's see which terms we just need to sort of gather the terms now together. So let's take a look. All right, so, and we can also write these things as higher powers too, right? So let's take a look. So I have a b. Where else do we need a b? We need a b with an xc squared. So I might have to choose another b over here, right? So let's look at this. Let me do the following. So I need to put an xc on the a. So let's do that. So we're going to have an xc on the a prime. So I put an xc on there, so I'm going to have to balance it out with an xc squared. So we're going to pull out an xc squared to balance that guy out. So let's do that. So I'm going to do that. I'm going to say this is equal to xc squared, and then an a prime times xc, because what do we know about xc? We know xc is a third root of unity, right? So if I raise it to the third power, I get back to 1. So that will account for this term over here, not that term yet, okay? Now I pulled out an xc squared. Now I also need a what? I need a b, but there's an xc squared b over here, right? So that's good. So I can use that xc squared b. And then an xc squared c. So that's going to give me a, so then I have this xc, so I could put a plus b over there. That's good, that's what I want. And then finally for the b, the xc squared a prime, I need an xc squared c. So I just need the regular c term over here. So this term over here, I need an xc squared. So if I put an xc squared, if I have if I have this xc times c, that's the same thing as xc squared times xc squared c. Now let's figure out why that's true. Because xc to the 4th power is xc. So xc to the 3rd power is equal to 1. So xc to the 4th power is equal to xc. Excellent. So those terms, so I've just used this term over here, and then this term over here, and then this term over here, right? So I've got those terms, and now I have xc a prime plus b plus xc squared c, so this bracketed term is equal to 0. Let's move on to the next terms. The next terms I need to use are a c, and then a b prime xc, right? So where's my b prime? So here we go. So this is a b prime xc. So I have a b prime xc. That's great. Then I have an xc squared a. Great. And then I have a c. So these blue terms over here, there's no modification that's necessary for them. So I have a c, and then I have a xcb prime, and then I have an xc squared a, like that. Beautiful. And those terms by this equation over here are 0, right? And then finally, last terms to do. So I'm going to need a xc prime c by an xc squared. So I'm going to pull an xc out of those terms, and I'll be left with an xc c prime. Good. That takes care of this term. then I will have an XCA, so it's just a plain old A, because I already pulled on XC. And then finally I have the B squared, so I'm going to put a XC squared over here with the B, so that's an XC cubed, and XC cubed is equal to 1, so that works out perfectly well. So in other words, I just rewrite this expression by plugging in some values of XC, and now this is the star equation, so these green terms are 0 by that star equation, these terms over here are 0 by the blue equation over here, and then these terms over here are 0 by the orange equation, so all this adds up to 0, so that proves that 3 times this expression is equal to 0, so our conclusion therefore is that g1 plus xc g2 plus xc squared g3 is equal to 0, and the triangle g1, g2, g3 is equilateral. And that proves Napoleon's theorem on triangles. Thank you very much.